In the chapter of cell, the unit of life, we will discuss about in this presentation about fluid mosaic model. The third model and the last model we will discuss in the last presentation. We discussed about unit membrane model and sandwich model. And in this presentation, we will discuss about fluid mosaic model and why this model was accepted and which properties were present that this model was accepted. Now we are going to start about fluid mosaic model. Fluid mosaic model was proposed by Singer and Nicholson. They were the two scientists who proposed fluid mosaic model. Composition is protein and the phospholipid, means plasma membrane is made up of or is composed of protein and phospholipid. If we talk about protein, protein is globular, means protein is round in shape, and two types of protein molecules are present, like intrinsic protein and extrinsic protein. In case of intrinsic protein is on the outer side and is loosely arranged, like here the lipid bilayer is present. So this is lipid bilayer. Intrinsic protein is if the protein molecule is between the lipid bilayer, like this. Then it is called intrinsic protein, and this intrinsic protein may be partially embedded or may be completely embedded. So here intrinsic protein is completely embedded, means it is all along the surface, whereas in case of partially embedded, if intrinsic protein is like this, is half the way, then it is called partially embedded, or you can say it is the partially embedded intrinsic protein. Whereas extrinsic protein is on the outer side, the protein is present like this on the outside of lipid bilayer and it is loosely arranged. Next is phospholipid, means phospholipid, you know that the phospholipid means with the lipid phosphate is attached, and phospholipid is amphipathic, means both hydrophilic and hydrophobic regions are present. And phospholipid molecule shows two types of movement. Number one is transition movement, number two is flip-flop movement. In case of transition movement is if the movement between the lipid molecule in the same layer, then it is called transition movement. And if in the flip-flop movement, if movement between the lipid molecule in the different layer, then it is called the transition movement. So if this is the one lipid layer, and if this is the one lipid layer, and if this there is a exchange between the lipid molecule in the same layer, then if this molecule is exchanged by this molecule, then it is called the transition movement. But if in flip-flop movement, if this molecule is exchanged by the lipid molecule in the another layer, then it is called the flip-flop movement. So these two lipid bilayer are facing each other and they held together by a force of attraction, and this force of attraction is weak force, and this weak force is van der Waals force. So between the lipid bilayer, they are facing towards each other, they held together and they have the weak force of attraction, and this weak force is van der Waals force. There is a definition for fluid mosaic model. Like fluid mosaic model states that a membrane is a fluidic structure with a mosaic of various protein embedded in it. So they also describe that the plasma membrane looks like a protein iceberg in a sea of lipid. Like you can say this is the diagram. Here you can say this is the sea of lipid molecules, and here the large icebergs are present, and these icebergs look like a protein. That's why the plasma membrane is uh, described as protein icebergs in a sea of lipid. So this is the plasma membrane structure fluid mosaic model. So plasma membrane, this is the intrinsic protein, and this intrinsic protein is completely embedded, and here the lipid bilayer is present. So this is the lipid bilayer, and here the head is present, here the tail is present. This is also lipid layer, and this is completely embedded intrinsic protein, and this is the partially embedded intrinsic protein, and this is the, and here this these are the extrinsic protein. And because this is the protein is present, if the protein with the protein carbohydrate is attached, then it is called the glycoprotein. And if with the, and here the cholesterol molecules are also present. So this is the phospholipid bilayer, and if we talk about only this, then it is the phospholipid molecule bilayer, because two layers are present. If we talk about only one layer, then it is phospholipid layer. If two layers are present, then phospholipid bilayer. And two types of proteins are present: intrinsic protein and extrinsic protein. Intrinsic protein may be completely embedded and partially embedded, whereas extrinsic protein is present on the surface. So in this slide we are going to discuss about why plasma membrane fluid mosaic model was accepted, because in this slide I have mentioned that plasma membrane should have these three properties. If these three properties are present, then the model can be accepted, otherwise the model can be rejected. And fluid mosaic, and why fluid mosaic model was accepted. So first property was selectively permeable, means plasma membrane allows the entry of water soluble and lipid soluble substances. So firstly we will start from lipid soluble substances, because in the unit membrane model and fluid mosaic model there was no problem with the lipid soluble substance, because plasma membrane lipid bilayer is made up of lipid molecule. If lipid is present, then there is no problem for the entry of lipid soluble substance. So here the lipid soluble substance is present. Now lipid soluble substance can easily pass through the plasma membrane and now has reached the internal environment. Now we are using the water soluble substance. For here the water soluble substance is present. So here the water soluble substance can pass through the head region, but here the hydrophobic tail is present, so the water molecule cannot pass through the hydrophobic phobic or tail region. So now in the fluid mosaic model, Singer and Nicholson uh, gave the solution, or gave the path, or for the entry of, or the for the passage of water soluble substances, because the water soluble substances cannot pass through this region. So here the intrinsic protein is present, and this is the completely embedded intrinsic protein. Now water molecule or water soluble substances can pass through this region, and now water molecules has entered the internal environment. So in the fluid mosaic model, first property, that is allow the entry of water soluble substances and lipid soluble substances, have been fulfilled. Next property is the variable protein to lipid ratio. In the unit membrane model and sandwich model, the scientists did not explain about this point, variability in the protein and lipid ratio, but the Singer and Nicholson explained the variability in the protein to lipid ratio, and how the lipid protein to lipid ratio is variable in a fluid mosaic model. So if this is the lipid bilayer, and you can see if this is the one lipid molecule, this is two lipid molecule, this is three. If we are going to take only this section, let me erase this, this. So we are going to take only this portion here, 1 2 3, and this I will write down this as A, B, C and D. So here 1 2 3 4 5 6 7 total phospholipid are 7 in number, and the protein is 1 2. So two protein molecules are present, so you can say ratio is 2 to 7. So in the earlier slide I discussed that, or discussed that protein, if lipid molecule, or you can say the lipid molecules show two types of movement. Number one is the flip-flop movement, and number two is the transition movement. So firstly, if there is a transition movement, or whether it is the flip-flop movement, because transition movement is in the same layer. If the movement is in the same layer, then it is the transition movement, and if the movement is between the two different layers, then it is called the flip-flop movement. So if there is a variability only when the molecule leaves its place. If this molecule or lipid molecule A leaves its position, and here the lipid molecule 3 leaves its position, when they are leaving their position, at that time there is no molecule at this, because before the exchange, if the lipid molecule 1 leaves its position and lipid molecule 3 leaves its position, after leaving there, after leaving their position, nothing is present at their position, because they are moving towards their designated position. So at that time nothing is present. So you can say, if this molecule has leaves its position, and now the lipid molecule A is here, and this molecule 3 is also leaves its position, lipid molecule is 3 is here. So now nothing is present here, nothing is present here. So now you can say here, at that time, 1 2 3 4 5 means at that time 5 phospholipids are present and 2 protein molecules are present. So now you can see the variability in the protein to lipid ratio. So you can see here there is a variability, because there was a transition movement, and now if there is a flip-flop movement, so if this is the lipid molecule 1 and this is the lipid molecule A, if the lipid molecule 1 leaves its position and lipid molecule A leaves its place, and they are going to exchange their position, now lipid molecule A comes here and lipid molecule 1 comes here. At that time nothing is present at their position. Now you can see there will be the variability, the ratio will be 2:5. Now earlier, when there was no movement, the ratio was 2:7, and at the time of movement, when they are moving, the ratio is 2:5, and after taking their place, again the ratio will be 2:7. So you can see there is a variability, means variable protein to lipid ratio. Now uh, there was, now if we use the protein molecule, and you can see here the protein molecule is present, and protein is here, the extrinsic protein is present. So here the extrinsic protein is present, and this is the carrier protein, and this extrinsic protein, or this carrier protein, needs to take something inside. So here the substance attaches to the intrinsic protein, and this carrier protein needs to take something inside the plasma membrane. Now this carrier protein leaves its position and goes inside the internal environment to escort the substance, and now this extrinsic protein is not at its position. Now there is a variability in also the protein molecules. So you can say the other point is also fulfilled, that is variable protein to lipid ratio. And if there is a variability, then the plasma membrane is dynamic, means there is a variability, means variable protein to lipid ratio. If there is no variability, it means plasma membrane is a static structure. But this model explained each and every point, like the plasma membrane allowed the entry of water soluble and lipid soluble substances, and if even Singer and Nicholson explained the variability in the protein to lipid ratio, and also they explained that the plasma membrane is dynamic structure, not static structure. And because of these three properties, because these three properties were present in fluid mosaic model, that's why this model was accepted, and the plasma membrane model is the fluid mosaic model. So the first two models, like we explained, unit membrane model and the sandwich model, were rejected because the models did not explain these 3 points in detail, and even they explained some points, even they did not explain some points But the fluid mosaic model explained these 3 points in detail, whether there is a lipid soluble substances can pass, then what is the pathway, or what will be the pathway for water soluble substances. So the water soluble substances can be passed through intrinsic protein, and they're also called channels. Means intrinsic protein is also called channel. And variable protein to lipid ratio means there is a variability. And how there is a variability? When protein or lipid molecules leave their position. If they leave their position, then some lipid or protein molecules are not present, then there is availability. And if there is a variability, then it is a dynamic structure, not static structure.